Aloha, Richard Halverson here. This is ITS148, and today is March 4th, Thursday, March 4th, and we are going to do video number 9 today, where we started. We had a class earlier this week on, let's see, Tuesday, I think, or probably on Tuesday, and we started chapter 15, searching and sorting, and today we're going to continue with chapter 15. So let me share my screen, and I'm recording. Okay, so we are it's March 4th, and so we are in this week. We're in chapter 15, and we're doing class 9 right now. All right, so let's go to Alima. No, let's go to the textbook. I hope this isn't bothering anybody. All right, so we're in chapter 15, and we started out Tuesday. We sort of introduced ourselves to what searching and, well, these are searching and algorithms, comparing a linear search with binary search. And then we defined this O notation, and we sort of learned the sort of rules, the two-step, more or less the two rules for determining what the big O of an algorithm is, and it's sometimes called the computational complexity, but basically it's a description or a factor. It's a term that indicates how fast or how much longer an algorithm takes to execute based on the growth of the size of the input, or based on the size of the input. So if the size of the input is 10, it takes a certain amount of time, and if that if the size of the input increases to 20, then how much longer does it take for the algorithm to execute? Is it twice as long, or is it 10 times as long, or is it only like a little bit more, or maybe it takes no more time at all? So that's what the big O notation is, and it's an important thing to figure out for your algorithms when you're writing new algorithms. And then we talked about how we analyze, and this is basically we talked about how we can actually analyze how long it takes the algorithm to execute based on steps. It's this rough measure of a step, and a step is like one comparison. It's like one assignment statement, and it's a way of sort of writing down in an expression or equation form how many steps your algorithm takes based on the size of the input. All right, so now we're going to get into sorting, and sorting is it's a algorithm, or it's a program, a type of program that is good for teaching computational complexity, because it's the big O, or the big O of a sorting algorithm is more than n. It can be n squared. So if something takes twice as long, or is twice the size of the input, it may take like 4 times longer to execute, and we'll see how we figure that out. All right, so so this is little participation activity that we showed last time, and it's basically sorting by swapping. And a lot of the sort algorithms use some sort of swap where elements switch places as the list becomes more sorted. And the algorithmic analysis has to do with counting the swaps, for example. All right, so this is a little game here where we're supposed to go along and let's see, what do we reset? Oh, select two numbers and swap. Okay, so I'm going to sort this. So let's see, there's a couple ways to sort this. I'm going to start by starting with the first position here and finding the smallest element all the way down here and exchanging this with the smallest element. And right now the smallest element is this one, so I'll swap it. Okay, now this first one has the smallest element, so let's go to the next one. I'll scan down here to see if I can find something smaller. I can't, so this already is the next smallest element. Then I'll go with the third one. Oops, no, I want to undo this one. Then I do the third one. I find the smallest element. It looks like it's this one, so I swap. Now the first three are sorted. Go with this one. I find the smallest element. It's this one. Swap it. Now these first four are sorted. This one, I find the smallest one. It's this one. Swap it, and it already knows it's sorted. So that's one way of sorting. And there's other swapping ways, which we'll see farther down. In fact, selection and insertion are both, well, selection, insertion, and quicksort are swapping kinds of sorts. And merging is a little different. All right, so the list is sorted in ascending order. So this just makes sure you understand the concepts here. The list is sorted in ascending order. 3, 9, 44. No, it's not because it goes up and then this goes down and then back up again. So anyway, you can do that. That's easy. All right, so let's look at selection sort. Selection sort is a sorting algorithm that treats the input in two parts. Okay, or it treats the input. Okay, the input has two parts, a sorted part and an unsorted part, and it repeatedly selects the proper next value to move from the unsorted part to the sorted part. So we start out with where everything is unsorted, and then we're going to start with the first one here, and we're going to do exactly the algorithm that I was doing up above. Okay, so we start with this position, and we scroll down, or we examine it. This is already sorted. Okay, let's run this and see what it looks like. Okay, so it's looking for something. It's going to loop. There's an outer loop here, and that's going to be I. And the outer loop starts and finds the proper element for this position. Then it finds the proper element for this position. Then it finds the proper element for this one, and then this one, and then this one. In fact, it only has to go in here because then the last one will be in its right place. But each time trying to find the right element that goes in this position, it's got to scan the whole rest of them. So to find this one, you have to scan the whole list, and then to find the next one, you got to scan the whole rest of the list. And so that's what takes the time here. So here it's going to, this is the smallest index, and it goes down the line, and it keeps on, it goes down the line, and it records the index of the smallest element. Okay, it records the index of the smallest element. So the first time it scanned down here, and it's the smallest element. It's the index of the smallest element that's smaller than the one that we're looking to replace. It's possible that this one is already the smallest one, in which case, as it scans down, the index of the smallest element is going to remain this first one, and there doesn't need to be an exchange. Okay, so it found the index of the smallest one, and now it's gonna swap them. So it has to use a temporary variable to do that. Actually, in Python, it does not need to have a temporary variable to do that. Python has that assignment statement where it actually swaps the values. It has the assignment statement where you can swap values. Okay, anyway, so you can see that this was written for other programming languages too. Okay, so now this one is in its right position, and it traded with this, and now it's going to increment I, and I is going to go to the next one. See, and then it's going to go down the line. Smallest, that's the smallest index. That's not. It's not smaller than this one. So then it exchanges those, and then I increments to the next index, and it goes through the same thing, finds the smallest one, exchanges it with 8, goes through the same thing, finds the smallest one, exchanges it with the 18, and then it's done. So that's how selection sort works. And advantages. Selection sort has the advantage of being easy to code, involving one loop nested within another loop. So you have the outer loop, which goes through all of the numbers up to the second to the last one. So I goes from 0 to the second to the last one. So it's going to go from it's going to start looking at that one. It's going to go all the way up to that one. So it doesn't need to look at the last one, because if all of these are in their right place, then this one must also be in its right place. All right. Now, and then from wherever I is, this inner loop goes from I plus 1 up to however many numbers there are. So there's 1, 2, 3, 4, 5, 6, 7, 8 numbers. And so I is going to go from, well, it starts with I plus 1. So that's why if I goes here, J is going to start here. And that's all it has to do, and then it checks that to see if the J index is smaller than the I index, and if it is, then it exchanges it. Now so to compute the algorithm is O of n squared. If a list of n elements, if the outer loop executes n minus 1 times, for each of those n minus 1 outer loops, there's going to be an inner loop that executes an average of n over 2 times. Why is it an average? Okay, anyway. So the total number, it's comparisons. Well, this is executes. I don't think this is exactly described correctly. But anyway, all right, so anyway, it's however many the inner loop is times how many the outer loop is, and they both depend on n. So the computational complexity, or the big O, is n squared, because you have an n here times another n here. All right, so when sorting a list of 50 elements, index smallest would be assigned how many times? Well, in this loop, index smallest is always assigned at least once for the range of numbers for n minus 1, for n minus 1. And best case is it goes all the way through here. It goes all the way up, and each one of these checks results in J not being smaller than the index. In other words, if it's already sorted, then this will never be true. So we will never be reassigning this index smallest. So this will never happen, and but still this always happens, and this is going to always happen n minus 1 times. So it's 50. This is 50 is n, so it'll be 49 maybe, I think. Yeah, the outer loop assigns. So anyway, how many times longer will sorting a list of 20 elements take than a list of 10 elements? Let's see, what happens if I put this up here? So 20 elements. 20 squared equals 400, and 10 squared equals 100. So it's 4 times, I guess. Oh. 4 times. How many times longer will sorting a list of 500 elements versus 50? Well, I don't know. 500 squared is 500 squared divided by 50 squared. And if we bring up a calculator, do I have a calculator? Here. 500 squared is 250,000. 250, can I move this like this? 250,000 over 50 squared. 50 squared is 2,500. So we end up going cancel, 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 cancel. 25 over 25 is 1. So this becomes 1. So it ends up being 100, I guess. Yeah, 100 times 250,000 over 2,500. There's 2 more zeros. So 100. All right. So anyway, that's selection sort, and so you should really go through the challenge activity, make sure you understand how to do selection sort. All right, insertion sort. Okay, so insertion sort is another swapping kind of. I guess it kind of bubbles. It's kind of like a bubble sort, but it the passes through the list are different. The algorithm for making its passes for swapping bubbling is a little different. So insertion sort is a sorting algorithm. It also treats the input as two parts, a sorted part and an unsorted part. And the sorted part is at the top or at the left, and the unsorted part is at the right. And so it starts out where everything is unsorted. So the unsorted part on the right is got all the elements, all the values, and the sorted part on the left is empty. And you start with the leftmost unsorted element, and you insert that into the sorted end at the right location. And since the sorted end is sorted, you start at the bottom, and you're able to bubble it up into its proper position. So let's see if this works. Okay, so I'm going to click on this, and it starts its. Okay, oh, unsorted. Okay, so it's gonna oh, you're right. It starts out where the first lowest element is a single element, and it is sorted. It's sorted because it's only got one element in it, then it is sorted. And then it's gonna see the 6. It's gonna, okay, the rest of these 6, 15, 3, and 20, these are unsorted. So it's gonna start with the 6 because it's the one that's closest to the sorted list. And it's gonna try to shift that 6 left into its proper position. So as it's shifting, if the element to the left is bigger, then it's going to trade places with it. And it's going to keep on trading places with it until the element to the left is equal or less than. So it's gonna, so the outer one is points to the next element that's gonna be, try to be inserted into the sorted list to the left. Okay, and then the inner loop is gonna be the sort of this bubbling thing where it compares two adjacent elements, and if they're not in the right order, it swaps them. And it does this while J is going to count down. J is the inner loop, and it's going to count down. J equals J minus 1. It's going to count down, and each time it's going to compare J with the one to the left of it. And if they're not in the right order, it swaps them. And it keeps on swapping until it is in the right order. And if it is in the right order, then it knows it's in its proper place in the sorted list, on the sorted list side. So if we keep on going here, it's going to do that one. It's going to end up trading places with the 6 and the 32 are going to trade places here, and that it uses this temp variable. I'm going to speed this up a little bit. And so now, and then J goes down to 0 and it's done. So it's done with this. And so now from index 1 to the left is all sorted. And next it's going to try index 2. And it's going to, so now it goes to the next one, and it's going to try that. It's okay. So no, then it's got a trade. And then it's going to compare 6 and 15. And they're already in the right order, so it doesn't have to do any swapping. And here it's doing, so 3 and 32, they're going to swap. And then it's going to go down to 3 and 15, and they're going to swap. And then it's going to go down to 3 and 6, and they're going to swap. And the last one, 20, is going to swap its way down to above 15, between 15 and 32. Okay. All right. So this shows the algorithm. This shows an actual program that you can copy into your, copy and execute. So there's a method here called Insertion Sort, which you pass in a list. Looks like this, an array, and it's numbers, and this will sort them. And it can sort them because when you pass a list as a argument, it's mutable. You can mutate it. It means that the if you're just passing a value to a method, then you're passing a copy of the value. So if you mess with it inside the method, you aren't messing with the original. Okay. However, if you pass a list as an argument, it passes the address of the list, and so it doesn't pass the list itself. It passes the address of the list, or where the list is, and the method can then go right in and manipulate that list. So that's why something like this works. All right. So this confirms your make sure you understand how insertion sort works. Given a list, what is the value that will be the 0th element after the first pass over the outer loop? So what's going to be this element after the first pass? I think it's going to be, this is insertion sort. So I guess it would be 14, right? Because we are trying to put this into this sorted list. And so all that's going to happen is this is going to bubble into place, and it's going to be before the 20. So the 0th element after the first pass in insertion sort, I believe, is going to be 14, whereas the first pass, the 0th element after the first pass for selection sort would actually be the 3 here. So anyway, so let's check and see if I'm right. Yes, good. All right, so this confirms if you understand that. Insertion sort runtime. It's the same equation. As selection sort. So insertion sort is good for almost already in sorted lists, for nearly sorted lists. So you can look at it and confirm that to yourself. So it's also good if you have if you have a sorted list and you're adding new things to it. So let's say you have a sorted list of employees or something, and you got thousands of employees or something, and you hire a new employee, and you want to put that new employee into the list, and then when you're done putting that employee into the list, you want the list to still be sorted. And so insertion sort is the best there, because you just you have the sorted list part, and then you have the unsorted list part, and that's the one new employee, and then that just gets inserted up into its proper place. So that's something to think about. Using insertion sort. So here we're analyzing the number of comparisons, and that's really what you should be doing with these, comparing things like selection sort and insertion sort. All of the O of n squared sorts. You want to look at the data to decide what the best one to use is, because then the average case is different depending on the data. All right, quick sort. Now I have to tell you, quick sort is the most intellectually difficult sorts to understand, and it's best written as a recursive program, and it's a swapping thing. And now that doesn't mean I've never written a quick sort program. Writing a program and getting it to work correctly and actually understanding the algorithm are two different things. And if you are given the algorithm, then writing the program from the algorithm is something that we all should be able to do. Writing the program from the algorithm is sort of the skill. That's the craft. It's like you can take the blueprints or the design of a boat, and then you can craft the boat. And it's one thing to be able to design the boat on paper, and it's another thing to be able to craft the boat. And these days you can find the plans for a boat any place on the internet. But if you don't have the skill to use the tools to make the boat, then you don't really have anything. And so, it is good. It's interesting, since this chapter is a lot more about algorithmic analysis. It's as much that as learning sorting itself. Quick sort is a good sort to look at, because I think average time is like O of n or something. It's the worst case is still, I think, O of n squared, but average is more like O of n. And does it talk about does it give the analysis here? Oh, quick sorts. Oh, I guess it's n log n. It's typically n log n. At each level, the algorithm does at most n comparisons. Okay, so let's kind of see if we can see how it works generally. It's a sorting algorithm that repeatedly partitions the input into low and high parts, where each part is unsorted, and then it recursively sorts each of those parts. So to partition, okay, so you have an input, and then you choose a pivot to divide the data into high and low parts. And the value of the pivot can be anything to start with. And then as you do this dividing, where you put elements that are at a higher index but lower than the pivot, they go to the lower part, and the ones that are higher than the pivot but are in the lower half, they get moved to the upper half. Or so sometimes you swap the pivot with an element, as you see. And so when you're all done, you have this pivot in the middle, and everything to the left, everything to one side is higher and everything to the other side is lower. And then you've got two lists that are half the size, and you do a quick sort. You do a recursive. You call yourself on each of those halves until you're down to two elements or one element that you easily put in order, and then, you know, as you bubble back up again, you end up in the end with a sorted list. So this little participation activity sort of demonstrates one pass. Okay, so when this is done, it's not sorted, but everything to the left is smaller than the pivot index, and everything to the right is larger than the pivot index. But it's difficult to follow. So it picks the midpoint, and then it's the pivot is 6, and then so we've got everything on the right is already higher than 6. On the left, though, we've got this 7. So let's see what it does. So that's the high and low, and so that is, this ends up being smaller. This is bigger than the pivot, and it's a smaller size, so it's going to have to do something about that. And then it goes to the top and checks that, checks that. So all those are okay. This is the pivot point. That's going to look like that. And so here's where we exchange these two, and then, you know, after that, we're basically done with this pass. And then we're gonna sort the bottom half next. So the pivot value is the value of the middle element. Index I for the low part begins at element I, and is incremented until a value greater than the pivot is found. So it starts here and it keeps on going up until a value greater than the pivot is found, or it reaches the pivot. And in this case, it was the first one. And then H begins at the top and is decremented until a value less than the pivot is found. And in this case, it didn't find one. And the elements at indexes I, L, and H are swapped, because this and this are swapped, and moving those elements to the correct partitions. So they're moved to the correct partitions. I guess the 6 was considered part of the upper partition. The partition process repeats until indexes I and H reach or pass each other, indicating all elements have been partitioned. So anyway, and then it recursively calls itself until all partitions are partitioned, and you end up with a sorted list. Well, I don't know. That's kind of tough for me to follow. It goes through some cases here, and it's probably okay. Well, you know, the idea is to learn the concept and how it works, so you can actually picture it happening in your head. And that's sort of the exercise. The idea that if you understand it well enough in your head, you could write the algorithm down, you know, from your head, and then presumably write code from that. There's some sorts you'll be able to do that, or at least if you work with this stuff a lot. Selection sort, you probably would be able to do that. You have to remember that you're storing the index of the smallest value as you pass down to the end of the list, and so on. And then there's another sort called a bubble sort, which is pretty popular, and it just involves exchanging adjacent. You just take passes through, exchanging adjacent adjacent elements that are out of order. by taking the passes through the right way, in the end you end up with a fully sorted list. All right. Okay, so you can go through these. At times it's 419. Okay, so here this looks at worst case. Worst case runtime for quicksort is O of n squared. Fortunately, this worst case runtime rarely occurs. So for typical unsorted data, such equal partitioning occurs. The quicksort algorithm's runtime is typically O of n log n. Quicksort has several partitioning levels. The first level dividing the input into 2 parts, the second into 4 parts, the third into 8 parts. At each level, the algorithm does at most n comparisons, moving L low and high, these low and high index pointers, indexes. If the pivot yields 2 equal sized parts, then there will be log n levels requiring n log n comparisons. And so this, you can test your understanding with this to the third. Yes, that's okay. So this would be 10, I suppose. For typical unsorted data, such equal partitioning occurs. However, partitioning may yield unequal sized parts in some cases. If the pivot selected for partitioning is the smallest or largest element, one partition will have one element and the other partition will have all the other elements. If this unequal partitioning happens at every level, then there will be n-1 levels yielding n-1 times n, which is O of n squared. So the worst case runtime is O of n squared, but that only happens if you're so unlucky that each time you pick a partition, it ends up being where there's only one element in one partition, or each time you pick a pivot point, there ends up being only one element in one partition and all the rest of them in the other. And so the chances of that happening are low. Okay, the chances are, it's on average, it's going to be more close to the middle, in which case we end up seeing more close to, log n comparisons. All right, so merge sort is an interesting sort. There's a sort concept called stability, or and what that is, if a sort is stable, then if 2 elements have equal value and they start out in a particular order, you could be sorting on some field in a record, okay, and then you have and then there could be other data in the record, and so if it's a stable sort, if 2 records, the field that is being sorted, the values are equal, the records will remain in the same order that they were in after the sort as they were before the sort. But an unstable sort means that they could switch places. It's still, the records will still be sorted according to the field that it's being sorted on, but you may not be preserving a previous sort on some other field. All right, so and it turns out that the O of n squared sorts are stable generally, and the O of n log n sorts are not. However, merge sort is an O of n log n sort that is stable, so that's what's nice, but it does require some extra space that you might not have. So merge sort is a sorting algorithm, and again, this is best thought of as a recursive algorithm. It's one of those few. Merge sort is a sorting algorithm that divides a list into two halves, and then it recursively sorts each half, and then merges the sorted halves to produce one sorted list. So if you have two sorted lists, it's easy to merge those two lists into two sorted lists into one huge sorted list. In fact, it just takes one pass to do that. And so merge sort takes advantage of that. So here's an example where you have six elements here, and you divide it up into you split it into two lists, and then you split it into two lists, and you keep on splitting it down until you just have until you're at the bottom and you've split it and you have two lists, but each list only has one element. Okay, then you combine them back up again, but combining two sorted lists is easy. It just takes one pass. So down at the bottom here, so this is splitting them down, and this is combining them back up again, and you end up combining the 3 and the 11, and that's going to be combined into a list that's 3 followed by 11, and then 8 is already a sorted list, and then those two lists are combined, and the 8 will be combined into the right place. First it'll grab the 3, then it'll grab the 8, then it'll grab the 11, and then on this side, first it'll grab if it merges this list with this list, first it grabs the 4, then it grabs the 18, then it grabs the 25, and we end up with that. And then here, it's got two sorted lists. So first it's going to grab the 3, and then it's going to grab the 4, and then it's going to grab the 8, and then it's going to grab the 11, and then it's going to grab the 18, and it's going to grab the 25, and we end up with a sorted list up here. So that's how merge sort works. So let's see this work. Oh, I see. So it figures out the middle, 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 and then it combines all the bottom nodes up, combines the 3 and the 11 up to, so I see, these are all the nodes. These are all the original nodes of the list. Combines those up, combines those up, combines those up. See, they're all leaves. You split until all the elements are leaves, and then you combine them up like that, and you end up with a sorted list. So determine the index J of the left and the right partitions. I don't know. 0 plus 4 is 4 divided by 2 is 2. 0, 1, 2. Is that it? Index J, so 2. Yeah. Right. All right, so you can see how that works. So here's the merge sort algorithm, and this is not this doesn't look like this is a recursive version of it, is it? Oh, this is okay. Anyway, so this test your understanding. This is test your understanding of. Okay, this is a recursive version. Yeah. Okay. So you can get that to run, copy it over, and okay. So it's 4:30, and so I think I've covered these algorithms. I've introduced them to you enough. You can read these and do the participation activities, and you know, you may be showing yourself the answer. You know, more times than you're comfortable with, but you know, that's one way of learning. And the idea here is that you understand it well enough so you can trace through this algorithm if you needed to. You understand it well enough so if you were to have to get this thing to work in some application where things aren't quite like this, but underlying in there, there's going to have to be some a merge sort, and it may be, you know, you're merge sorting a bunch of records, and it's one particular field that you're sorting on, or it could be a nested sort where you got, you know, primary, secondary sorts, and you understand the algorithm well enough to be able to take it and get it to work in your application. So next time, I think I will do however long it takes me to do lab 1510 and 1511, but I will come back in the next video and do those labs for you. So this concludes the discussion of the chapter of the chapter 15 textbook sections, and we'll finish up the labs next time and then go on to lists, stacks, and queues later next week. Thanks for watching.